Okay. So, just to recap what we've talked about so far, we've talked about design-based inference, we've talked about a definition of complex samples, and we've talked about appropriate design-based analysis approaches and model-based alternatives. But our focus moving forward is going to be on design-based analysis. Okay? So before we jump into examples, I just want to talk about, again, the implications of this decision to ignore sample design features versus account for them when you do analysis, and see how often this actually happens in practice. Okay? So a failure to conduct these kinds of design-based analyses when your objective is finite population inference, and you want to account for these design features, can lead to erroneous conclusions about the populations that you're talking about, and ultimately incorrect inferences. We're going to see some examples of that coming up here. So if you think about this larger total survey error framework that captures all the possible ways that a given survey estimate could be shifted away from the population parameter that you're trying to estimate, an additional piece of that framework is analytic error. And so the idea there is the people designing a given survey could be very cognizant of the total survey error idea. They could minimize sampling error. They could minimize non-response error. They could minimize measurement error. They could minimize processing error, give you a perfect survey data set that, if it's handled correctly, gives you the right population quantities. But when that data set gets handed off to a secondary analyst who is not responsible for preparing the survey data set, if that analyst completely ignores all the features of the sample design, all the work to minimize all the other sources of survey error is wasted. That's the issue here. Okay? So analytic error defined is when people take a survey data set and in that analysis, they fail to account for features of the design that affect the quantities that they're trying to estimate. And that's another piece of this larger total survey error framework, all the different components of the error in a given survey estimate. Okay? So the issue here is that secondary analysts without training in these types of analytic approaches may end up applying standard methods to complex sample surveys, and when they write papers, those papers might be prone to erroneous inference. And it's especially dangerous if the people reviewing these papers aren't aware of these issues either. So it's very easy for these issues to get through the peer review process without being caught. And I'll talk about some possible solutions for the research industries in general at the end of this discussion. But that's the issue that we're focusing on here, this issue of analytic error. Okay? So again, if secondary analysts ignore these features of complex sample designs, whether they're taking design-based or model-based approaches, survey estimates could be erroneous. So for example, weights are designed to give you unbiased estimates of what's happening in the population. Stratum codes give you that increased efficiency of the estimates. Cluster codes capture losses in efficiency due to cluster sampling, increased standard errors. So a failure to account for these features in analysis negates all of those resources that are dedicated to minimizing these other sources of total survey error for a given survey project. Okay? So it does put the onus on analysts to be careful when analyzing these kinds of data sets to make sure that you're not adding another source of error to the estimate. Okay, so research on this kind of analytic error goes all the way back to Ed Deming. Some of you may have heard of Ed Deming. He's kind of a godfather of quality control. He revolutionized the way that Japan makes automobiles. Okay? So he was very important in quality control, and back in a 1944 paper in American Sociological Review, he kind of came up with this taxonomy of all the different sources of error in a given survey, and a key source that he focused on was errors in curve fitting and other related errors that can arise in the approach that someone takes to analysis. So this is by no means a new idea. Like from the mid-1950s all the way up to where we are right now, there have been a variety of frameworks proposed for total survey error. And the inclusion of analytic error as a form of total survey error goes all the way back to that paper. Okay? There's been more of a recent focus on it. So Tom Smith, in the 2011 paper, he formally defined analytic error as an important component of total survey error. That is, what the secondary analysts are doing with the survey data. Okay, that could be adding another source of error. Okay? So in a book that came from a conference on total survey error, we did kind of a pilot study. Back in, I think, about 2013, there was a general forum discussion at a workshop on total survey error where we talked about this analytic error and said, people have been philosophizing that it's an important part of total survey error, but nobody's ever looked at it. So we did this little pilot study where, with some graduate students, we looked at 100 peer-reviewed journal articles that all presented secondary analyses of survey data. So all of these studies downloaded survey data sets that had a public health focus. So these are data sets like the National Health Interview Survey, National Health and Nutrition Examination Survey. All these health surveys, we downloaded the articles. And then we looked at what they were saying they did for their methods in that particular paper. So what approach did they take to analyze the data? And I boldface and underline a parent because we're going based on their methods. Many of these papers, it was before a time where code is now often required for publishing a secondary analysis. You show your code that you use. Many of these articles, we couldn't find code. Some we could, but many we couldn't. Okay, so I say apparent failures to account for weights and complex sampling features, like we talked about with stratification and cluster sampling, were very common. Okay? There's a little bit of an alarm to us. And again, I mentioned, do the authors ultimately provide code for proof? More journals are starting to ask for this. But when we did this study, it wasn't quite as common. But it was clear in method section that there were just no references whatsoever to these techniques or the need to worry about weights or anything like that. They say, we fit a linear regression model. We calculate descriptive statistics, so largely model-based techniques. Okay? Furthermore, subpopulation analysis, when people are focusing on very specific subpopulations, elderly white females or something like that, are rarely performed correctly in design-based analysis. That's another major shortcoming here that we saw within the literature. So as a pilot study, this kind of set off some alarms, and it motivated a larger study that we ultimately submitted to NSF. Okay? So when we wrote this proposal to NSF, our question was, how big of a problem is this in terms of research in general? So what is the prevalence of these kinds of apparent analytic errors in peer-reviewed journal articles, conference presentations, book chapters, and technical reports that are taking advantage of survey data? Okay? Have there been trends across the decades in the prevalence of these errors? So are more and more people learning about these techniques and the apparent rates of the errors going down? Do journal-specific features dictate the error rate? So things like impact factors, having statisticians on the editorial boards, guidelines for the use of survey data. What are the implications of making these kinds of errors for estimation and inference? So if a paper says that they blatantly did not use the survey weights, well, what would happen if we went back and computed those same estimates using the weights? Do they change? And then, do the same problems exist not just for surveys of human populations, but for establishment surveys? Many surveys are done on establishments like businesses, farms, schools, things of that sort. Do the same issues exist for secondary analyses of establishment survey data? So these were kind of the 5 broader research questions that we wanted to answer with this particular proposal. Okay, so fortunately this work was funded by NSF. And in this work, what we did is we drew a stratified sample of 150 research products that analyzed survey data from what's called the Science and Engineering Statistical Data System, or SE-STAT. So this is they wanted us to focus specifically on a major government survey program. This is the program that produces data like the National Survey of College Graduates, the Survey of Doctorate Recipients, so this is in kind of an educational area. And what we did is we organized Google Scholar searches of published articles by decade. And then we did systematic sampling of articles within that decade so that we made sure we had good representation from the entire time frame. And we sampled 50 of these products that presented secondary analyses, so that was an eligibility criterion, is that the published paper had to say that it was doing a secondary analysis of one of these data sets. And then we scrutinized these articles to see what exactly the authors were doing within these articles. So each of the 150 articles were coded on these items here. So the year that it was first available online for the decade analysis, did the analysis account for the weights? So did they explicitly say in their method section that we accounted for the weights that were available in these data sets? Because all 3 of these data sets have all those features that we were just talking about. Okay, so it's important when working with them to account for these features. Did the analysis account for design features and variance estimation? So again, did they go to steps 1 and 2 in their analysis? Did they take a design-based or a model-based approach? Did the authors use appropriate software? Did the authors perform appropriate subpopulation analyses? Again, for this design-based approach. And then for the journal articles, what was the impact factor? We went to the websites of these journals and said, were there statisticians on the editorial board? Were there guidelines provided for secondary analysis? All of these different things were coded for each of these 150 different products. Yep.
Could approaches be both design-based and model-based?
Yes. There are so-called hybrid approaches. So the question was, could you have an approach that's design-based and model-based? A good example of that is weighted multi-level modeling. So you're fitting a multi-level model. Your inference is with respect to both the model and the sample design. So we'll come back to that a little bit later. Yep. But yeah, you could have both design-based and model-based analysis. Okay. Then after we coded all those research products on those different indicators, we looked at the implications of making these analytic errors for analyses of these types of data sets. So we downloaded the public use data files, the same data files being used in some of these articles. We obtained the replicate weights. So this agency makes replicate weights available for variance estimation. Okay? And then we reviewed the sampled articles with the NC-SES staff to identify descriptive estimates that would be of interest to data users and regression models that would be of interest to data users. So we worked together with the program officers of these different surveys to try to identify stuff that the users are really doing a lot. A lot of this was informed by the articles that we ultimately sampled. Okay, so in terms of this implication step, we performed 3 types of analyses for both descriptive and regression parameters. So we fully accounted for the design features, like I was talking about with appropriate design-based analyses. We accounted for the weights only, still using linearization for variance estimation. And then we ignored the complex sampling features entirely. So we want to see what would happen to our inference across these 3 different approaches. Will we reach different conclusions? Will we paint different pictures of the populations, and so forth? And we looked at ratios of these variance estimates to assess what the survey literature generally calls misspecification effects. And that's where you misspecify the variance estimation model. So you ignore the stratification and the cluster sampling in this kind of analysis. Okay, so we looked at what happened to the variances in addition to the point estimates. Okay, so this table just shows the results of that initial meta-analysis where we coded these 150 different products. Some products had to be dropped because they were ultimately not eligible or they didn't contain enough information or we couldn't make a decision about what they were doing. So you see the total N was 145 different research products. So the first indicator is a simple indicator of whether or not they explicitly state that they accounted for the weights in analyses. And you see the overall estimate there is 54.5% of the articles. So within the confidence interval, you can say that half of these published reports ignored weights with everything that I just said. Okay. Accounting for complex sampling and variance estimation. Horrible story here. Okay. I mentioned that this is happening a lot. Our fears were realized. Okay. So even if people said they were using weights, less than 10% of these articles are saying they're using something like linearization or replication techniques or anything like that to actually estimate the standard errors. So all that stuff that we just talked about, stratification, cluster sampling, effects of weights on variance estimates, ignored. 93% of the time. Okay. Using design-based approaches, about half explicitly said that they were using a design-based approach, and that kind of overlaps with the weights. They were saying, we used the design-based approach by incorporating the weights in the analysis. Hopefully now you realize that is an incorrect statement. Okay. You can see those numbers almost match up exactly. Okay. Subpopulation is another critical issue. 10% doing this correctly. So the issue there, what I keep saying about subpopulation, long story short, don't delete cases that are not in your subpopulation. Okay? Keep all of the cases in your data set and just use a simple indicator, 1, 0. Is a case in your subpopulation or not? If you physically delete cases that are not in your population, you run the risk of physically deleting sample design information. And if there are sampling zeros, meaning that there's a cluster that had no subpopulation whatsoever in it, that's fine, but it should be treated as a 0. It shouldn't be deleted entirely from your estimation. That's the issue here.
So with regards to subpopulation analysis, isn't that a substantive question of interest, whether the results differ by gender? So
Sure.
Something like that. So, but what if you're not interested in that, or there's no theory to back that up? So why would you even do it?
So again, like back to my earlier example, you want to make all your inference about a population of, say, older white females. Okay? And suppose there are 30 clusters and 15 strata in your design. So you physically delete everyone who's not an older white female from your data set. And you look at your design features, now you have 27 clusters and 12 strata. You physically deleted 3 clusters where there were sampling zeros. There's no sample present. But in terms of your variance estimation, those zeros should be accounted for in the variance estimation because the random process didn't produce any subpopulation from those 3 clusters. You physically delete those, you no longer have a valid standard error. What's even worse is if you have one of these designs where you have 2 clusters within a stratum. You need at least 2 clusters within a stratum to estimate variance using these techniques, because variance is based on the clusters. If I only have 1 cluster in a stratum, I can't estimate variance. So what happens is if you have that 2 cluster per stratum model, and you physically delete one of those clusters, some of the software like Stata won't even give you a standard error, let alone it being incorrect. Stata will flat out stop and give you a missing value for the standard error, saying, I need at least 2 clusters in every stratum. So when you physically delete, you run into that problem. As an analyst, all you have to do is create that 1, 0 variable and plug it into the procedures.
Conceptually, this matters only if you have data points that aren't in the target sample population.
Yeah.
Right. Okay.
Which I would argue is 100% of secondary analysis.
Got it.
So it matters all the time. Okay, so that's an issue as well. And again, the issue there is when you say you're doing a subpopulation analysis, just say you formed an indicator and processed the entire sample before focusing on that indicator. That's the critical step there. Okay? And then another issue is with respect to language. So one of the things we coded was when they describe their results, are they talking about X% of the sample had this feature or an estimated X% of the population had this feature? One of the nice things about using weights is that it gives you the power to make statements about populations. You have the power in your hands to say, I estimate 45% of this population had a particular disease because you're using weights that were designed for that purpose. So it's completely incorrect to say 45% of my sample respondents had that disease. That is misleading. Okay? So that was one of the things we coded. People were generally doing that right 3/4 of the time, but still about a quarter of the articles, they're saying things like 45% of my respondents had this characteristic. You have the ability to talk about that larger finite population when you use these weights. So take advantage of it. That's the key here. So alarming stuff, really, this took 2 years to code these articles, at this level of detail and understand what was going on. And it's just really quite shocking. And I'll provide some other evidence here in a second. Okay. This is the trend plot. So we broke this down by decade. Remember, we coded the articles by decade. So the upper left plot is the probability of using weights in the analysis. Okay. You see it hovers at about 54% with some variation, regardless of the survey. So the 3 lines are for the 3 different surveys. Some surveys it actually drops down to about 20%. And it's not just in the older decades, it's now. Like articles that have been published using the NSRCG, for example, 20% were saying they use the weights. In articles that were published after 2010. Right? So it's not like it's getting better. In some cases, it might be getting a little bit worse. Probability of variance estimation, that's the top right plot. That's just shocking to me, quite honestly, because it's not like this is new theory or these are new techniques, okay, to estimate sampling variance, and it's below 10% consistently, regardless of what the decade is. Okay? Subpopulation estimation in the lower left, and then describing the population correctly in the lower right. So there wasn't a lot of variability between surveys based on these coded data. And it doesn't seem like there's a trend that's improving. So the question then becomes, like, what should be done to battle this? Whether it's journal guidelines or minimum standards or better data documentation for these different surveys that are publicly available. There are a lot of potential paths or ways that this could go. So this just kind of summarizes. Another interesting thing is that, I said 10% roughly were reporting correct variance estimation. Peer-reviewed journal articles were the least likely to do variance estimation correctly. It was more commonly reported as being correct. We used the jackknife, we used linearization in conference presentations. What I'm saying, this is getting through the peer review process, where standard errors may be completely incorrect. Model-based approaches tended to ignore design features entirely. A lot of the articles made vague references to robust standard errors. I don't know what that means. I can compute a standard error. I can label it robust. What does that mean? What did they actually do to compute the standard errors? This was usually just a footnote in tables. We didn't know how to code them. Almost no references to the use of appropriate software procedures, like we're going to be talking about today, like the survey procedures and different packages. And we also found that journals almost never provide guidance with regard to secondary analysis of survey data, guidelines, where if you're going to try to submit an article that's presenting secondary analyses, at a minimum, you have to demonstrate via your code or something else that you've accounted for these design features if you're taking a design-based approach. So we're on kind of a little grassroots thing right now to try to get that going in some more quantitative journals.
Great.
Yeah.
I'm just wondering on that point about the journal articles being less likely to use the design characteristics appropriately than the conference presentations. If there's actually either direct pushback on the part of the journals or indirect pressure to keep within a certain word limit, and like, did you actually code whether there's like a footnote saying like we tried this with?
Yeah, we really scrutinized those articles, and when we found code, we looked at that to see what they were doing. So that was a great situation, but code wasn't available in every situation. So, ideally, you'd want to go back and see the code that they were using. That's why we emphasize a parent, because word limits may have prevented them from saying, we use Taylor series linearization, and we use weighted least squares, or whatever it was. Certainly that's possible. But at a very bare minimum, you could dedicate 2 sentences to just saying that you use these kinds of approaches. It doesn't require a word salad. Okay, so what happens? We said we coded this kind of apparent problem. What happens when you actually look at the problem? Okay, so in the survey of doctorate recipients, we found that inferences related to estimated distributions for the target population would change for 5 of 8 categorical variables. Like something as simple as a descriptive table. The confidence intervals would no longer overlap for 5 of the 8 variables if the design features were ignored. Okay? In the NSTG, different survey, among 10 continuous and categorical variables, there'd be substantial changes in inference for 9 of the variables. 90% of the descriptive estimates would lead you to a different story about the target population if you completely ignored these variables. I'm going to show you some examples. Okay, here's an extreme. So the National Survey of College Graduates, they actually draw their sample from the American Community Survey. Okay, so that's like a frame for their sample design. In their documentation, they explicitly say that they are oversampling people whose primary job is in science and engineering. That's part of the sample design. Back to Jeff's earlier comment, they explicitly say we oversampled people with jobs in science and engineering, okay, to try to make sure that our sample sizes were large enough for research on that subpopulation. It's clear as day, right up front in the documentation. Okay? When you actually analyze an indicator from the NSCG of whether your primary job is in science and engineering, which is a key indicator for data users of this in this world, If you fully account for complex sampling, your weighted estimate of the proportion of the population with a primary job in science and engineering is about 30.4%, with a rather small standard error. That's fine. Seems reasonable. If you only account for the final weights, notice the standard error goes up a little bit. You're not getting the gains from the stratified sampling that was actually used, but that's minor. But look what happens for the 45% of the articles that are completely ignoring the weights. That simple descriptive estimate jumps to 55%. So you're going to write an article that says that 55% of this population, the NSCG population, has a job in science and engineering with that small of a standard error, even smaller than the 0.3, and be done with it? That's the shock, and we're finding that that's happening about half of the time. Now, not every estimate is like this. This is where the weights were highly correlated with the survey variable, as said in the documentation. They said they oversampled people with a job in science and engineering. So clearly, the weights account for that oversampling. But if you ignore those weights in computing descriptive estimates, which is happening half of the time, this is what could potentially happen. So this is an upper bound, I mean, at least in terms of what we saw, but a 25 percentage point shift in the point estimate if the weights are highly correlated with the variable that you're analyzing. And weights were highly correlated with several other measures like race, ethnicity, your degree, your salary, your major degree, all of this because of the way that they did the sampling, the oversampling that was actually done. The weights have a reason. There's a reason why people spend so much time preparing them, making them available for analysts to use. So again, as a secondary analyst, key thing, look at the correlations of your weights with your key variables before you jump into any kind of analysis. Just an absolutely essential step, simple to do. There's really no excuse not to do that when you're sitting down with one of these data sets for the first time. Okay, what about regression? So we looked at descriptive estimates. We fitted a logistic regression model to a binary indicator of having a large annual salary, above $150,000. And one of the coefficients that the program officer said would be of interest to data users is whether there's an interaction in terms of predicting high salary between your major degree and race ethnicity. In other words, race ethnicity moderates the relationship of your major degree with the probability of having a higher salary. So it's a question that a lot of the users were looking at. So if you do a design-adjusted analysis, fully accounting for the complex sampling features, you find evidence that this interaction actually matters. You can talk what you want about p-values, but there's evidence at about a 5% level that this interaction matters. Okay? If you ignore the stratification in the analysis, you only were to use the weights and do the exact same test with the exact same sample size, look what happens. At no level could you argue that that interaction matters. What happens if you ignore every feature? Same conclusion. Okay? So people might think that this is important, but then if they ignore the features and they don't get the benefits of the bias correction due to the weighting and the stratification as well, you arrive at completely different conclusions in these regression models of substantive interest. So in this case, the weights, again, were informative about this relationship, and the stratification helped in terms of the precision of this particular estimate. Now, this didn't happen a lot. There were no major effects on an ordinal regression model, for example, of hours worked per week, if we predict that with race, ethnicity, job type, and the interaction of those two. So we tried a number of these different substantive models in each of these different survey data sets. Here's another example. If you fit a regression model to log transform current salary in the National Survey of College Graduates, and you look at the main effect of having a science and engineering degree, you fully account for the complex sample, clearly it matches. Okay? Science and engineering degree tend to have a larger salary. If you ignore the weights and you ignore all the sampling features, look what happens to that coefficient. Keep in mind that this is log transform. Okay? This difference would be even larger if we were looking at it on the natural scale. Okay? No evidence whatsoever of a relationship. So if you ignore these design features entirely in estimation, you would write in your paper, unfortunately in this population, it doesn't seem like having a science and engineering degree matters. The current salary. Then you get all these letters to the editor saying, what are you talking about? Like, we have this huge scope. You know, you can see where this goes. As they can emerge. Okay? Same, another example in a logistic model for another interaction, fully accounting for the design features, no evidence that the interaction matters. You ignore the design features, looks like it's a huge finding. So it can go any direction. Right? This is why it's so important to account for these things. Okay, so this just kind of summarizes what I was just talking about now in public health and in this kind of education setting. So again, we found this issue with a failure to account for the weights a lot of the time. These results were largely consistent with that initial pilot study where we focused on public health publications. We did find that having statistical reviewers helped in reducing errors. That was one of our relationships that popped out from the meta-analysis. So again, that speaks to things that journals can do to kind of prevent this from happening. And again, implication-wise, failing to account for these features can lead to some very severe problems with what you're computing. And again, the common theme is that all of these problems arose when the weights were highly correlated with your key variables. So very important to evaluate that before you get started with the larger analysis. And if people fail to account for the stratification, there are gains in efficiency that can be missed by failing to account for that when you're estimating your standard errors. Okay? So NSF said, that's nice. You guys can do this for human populations. What about establishment surveys? Okay, so that was another aim of this particular grant. So we looked at data from an establishment survey that the Census Bureau conducts. And what we did is we looked up, to begin with, highly cited publications that present these kinds of secondary analyses of establishment survey data. So not human populations, but establishment surveys. And then looked at what happened in this particular survey as an example of what the implications can be. That was kind of our two-pronged approach to the establishment surveys. We again just used Google Scholar to locate some highly cited articles that presented secondary analyses of these kinds of data. Then we looked at analyses of the Burtis data, kind of the same 3 different types of analyses that we talked about for the other 3 surveys. And again, we focused on what would happen. Burtis and most establishment surveys, they don't use cluster sampling. Because in establishment surveys, the clusters are the units of analysis. So usually what they do is they stratify. So the designs are purely stratified, and they may involve weighting depending on oversampling. So we really focused on whether or not people accounted for stratification as a design feature. This is a Burtis disclaimer, so this is a very protected, restricted use data set. So just to be fair, make this disclaimer clear here. So we had to go through a very rigorous review process with the RDC that's in the basement just to try to get output out. Like they made us go into SAS output and remove significant digits from the SAS output. Like that's how protected this is. So I want to make this disclaimer very, very clear here. Okay, the meta-analysis was completely frightening. So we found the 10 most highly cited articles at the time on Google Scholar that presented secondary analyses of establishment survey data. Okay, median citation count was 413. That's the median of these 10 articles. These are articles. Not books, these are articles. Okay? Median impact factor of these articles, about 3. Okay? Of those 10 articles, 2 of the 10 even mention using weights at all. Median citations, 413. 8 out of 10 did not use the weights in estimation. It's stunning. None of the articles, 0, mentioned accounting for sample design features, stratification, when estimating variances. It's all purely model-based. Okay? And like we've said, that's fine for regression models in some cases, but if you're talking about descriptive estimates, things can really go wrong if you completely ignore these weights. Yep.
This probably speaks to that issue you raised before about economists having this predilection against using weights. This is a survey that economists tend to use. So what is their argument in rationale against using design-based?
For models, I can understand. We're going to come back to that later. For fitting regression models, there's an argument. For descriptive estimates, I don't know what the argument is. I can't support it. I don't understand. It makes me
I'm thinking application of their argument about models to descriptive data.
If you present, maybe you're presenting like a mean predicted value based on a model, but if they're presenting just frequency tables and means, there's no argument. Especially with this kind of oversampling, it's scary. And that all these articles presented descriptive tables. I mean, I don't know what to say. Like, it's just kind of mind-boggling. So, there's a lot that can be done to try to trim this problem. Yep.
Well, I hold a bachelor in economics and a master's right now. But I think like these topics are not like part of our
They're
like
not.
most of the time when we take courses, we are taught like what happens when the assumption of the model are violated. And we can do stuff like account for the toxicity, collineality, but never about like survey design. Like maybe this is why we have been ignoring.
Yeah.
But yeah.
But that, again, that's for regression models.
Yeah.
Like, I think the larger problem is just if there's a focus on descriptive estimation. You can just paint completely different pictures of a population if those weights matter for a descriptive estimate and they're not accounted for. I think that's the larger problem. I can understand the model argument. Like, if you think you're doing a good job of fitting the model, fine. We'll come back to that. But my bigger concern is with descriptive stuff, which is what a lot of us focus on, data producers, in trying to describe populations. So, not great. What about implications? So I mentioned 80% not using the weights. We took the Burtis data, and there you see that column of sample sizes. That is the significant digit removal. Like if the sample size was like 31,235, the RDC coordinator was like, nope. Had to be cut back to 2 significant digits. Anyway, those are the sample sizes. And you can see the 3 different approaches for this establishment survey. So approach 1, ignore the weights, ignore the strata. By far and away the most common approach. Okay? Approach 2, account for the weights, but ignore the strata. Approach 3, account for everything. So all we're showing in this table is for 4 key variables: total salary expenditures of these businesses, total worldwide employees, total U.S. expenditures on R&D, and total worldwide expenditures in R&D. We're just computing means. It's something very simple. Look what happens to the estimates because of the weights. 80% of the time, this is what's being reported. Look at the total salary expenditures in millions. If I ignore the weights entirely because bigger establishments are sampled at higher rates, looks like a pretty big number. Once I account for the weights, how many fold difference is that in terms of that simple descriptive estimate? And again, we had to show our code. We had to show exactly how we got here. That's all part of this paper. We're not just making up numbers. This is using the data that's available and the weights that are provided to compute these values. Okay? Same thing for employees, expenditures. The story doesn't change depending on the descriptive estimate. That's why I think it's a bigger deal for descriptive estimates. But what about regression models? Okay. Here, the dependent variable was U.S. research and development expenditures, and the predictors were salary expenditures, worldwide employees, and the interaction between those two. The intercept in this model related to the descriptive stuff we were just looking at, right? The regression coefficients, not huge changes, but look at the coefficient for total worldwide employees. It changes in magnitude by 1,000 once you account for the weights. So coefficients might not be as heavily affected as descriptive estimates, but they can still be affected. Look what happens to the standard errors. All this stuff. I mean, this was now establishment surveys. So again, very important to at least consider what happens to your estimates when fully accounting for these design features. Okay, so failing to account for the weights in the Burtis led to substantial changes in inference for both means and regression coefficients. And a failure to account for the stratified sample design led to overly conservative. Okay, so those standard errors went down when fully accounting for the complex sampling features, including stratification. Okay, now you might say, oh my goodness, enough with your studies. Like, clearly you have an issue with economists. Like, what's the issue? So this is not just me. So JAMA just put out the exact same kind of article. Okay? So Kara et al., I'm happy to share the article, did an observational study of 120 out of 1,082 published studies. These are peer-reviewed journal articles. They were published in 2015 and 2016 using the national inpatient samples. Anybody worked with those data before? NIS? Big data set of inpatient visits, quoting various things that happened during those visits. Of the 120 studies that they coded, 79 ignored everything. And they coded code. They went above and beyond what we did. They coded in journals that require the code to be shown. 79 out of the 120 studies didn't account for any of these things, let alone just the weights. So it's not just me. This is a problem that appears to be happening in multiple fields, multiple different types of survey data sets. And again, it goes back to a mix of what's being taught in graduate studies, what journals are expecting or what journals are requiring that people publish. But every time that we talk about this with colleagues and so forth, all we can really say is we are hoping that you guys, after hearing about this kind of stuff, can spread the word to your colleagues, to editors that you might work with. Like, it really needs to be a movement to keep this from happening, because in terms of the total survey error framework, you could spend millions and millions and millions of dollars collecting data. But if the secondary analysts who are writing the papers that are getting that survey out in the public eye are making these errors, and they're saying that this survey says that this happens about this population, and it's all biased, what are we really doing? That's the issue here. So, implications, I just say yikes. Okay, this is one survey data set, of course, but at this point, hopefully you're getting the picture that if we were to repeat these kinds of studies for a variety of different surveys, we're going to have some issues. So, a lot we can do to fix this problem, and it's mindlessly simple in the software to prevent this kind of stuff from happening. Okay? So, at this point, well, let me pause. Are there any questions about that analytic error investigation that we just went through? Any questions, comments, thoughts? Any chat questions, Jim?
The inputs is so correct.
I mean, my view on this is that, especially for these highly cited articles, I mean, if we really wanted to be dicks about it, excuse my colloquialism, like we could have gone to these 10 journals and said, for the establishment surveys, and said, there's a problem. Like, reevaluate these papers. We didn't do that. I mean, you could consider that potentially career suicide, but one way or another, I think it needs to happen. Like, if it's not retraction of papers, it's, again, introducing minimum standards for what journals can accept if you're going to use a secondary analysis. I mean, it's an idea, but if you guys are reviewing papers now, and you're reading about secondary analyses, and you have some sense of these issues now you can ask that question at the review stage, at the peer review stage, and say, wait a minute, like, did you guys fully account for these features? Did the weighted estimates vary from your unweighted estimates? These are the kinds of questions that you can now ask to make people show that they've at least considered these design features in their analysis and the implications of accounting for these features. Yeah, question.
So I'm coming from the field of genetics and neuroimaging where there's like no population-based surveys. So would you say that even using any kind of population-based survey is probably better than?
Well, there's all kinds of issues in genetics right now, and we're actually, like, as we speak, somebody's writing an R01 to reevaluate how genetic data are processed and potential selection bias in these kind of genetic samples, because you have a very specific kind of person who participates in these genetic data collections, and then there's so much being done with those data where it could be a very poor reflection of what's in the population. So that's just a wide open area for research, and the survey methodologists upstairs are currently worried about that, and they're working on these kinds of ideas for how to change the way that those genetic data are handled in terms of analysis, given that so many of them come from volunteer samples. So it's a wide open problem. Yeah. Okay, yep, David.
Early on in your description of this, I think you talked about someone pulled from the ACS survey.
Yeah.
Particular job category.
Yeah. Yeah.
So in that case, trying to put this all together, when they did that, do you know if they dropped or they created that?
No.
Not better.
Yeah, so for those surveys that I was talking about, they treated the ACS as a frame. So they literally treated the ACS as a population frame, and they sampled from ACS respondents. So in terms of their sample design, they drew the sample for those surveys from ACS respondents. So that this wasn't an issue with analysis. That's just how they designed the sample to get to these other surveys, and SCG in particular.
Not an extra.
No. No, yeah, it was a sample of respondents in ACS.
If you did do an extract for occupation.
Yeah.
In that case, should you do a,
If you're using ACS data
yeah,
and you're looking at specific occupations, in that case, it becomes a subpopulation analysis.
right,
So that's where you have to use that technique that I talked about earlier.
right.
Yep. Yep.
Thank you.
Okay, so let's start to get into some examples, since I know that's what many of you are here for. So given this massive problem in the JAMA article about the 2000, or about the NIS data in general, we started with some initial examples of what can go wrong in the NIS data if these things are being ignored, just to kind of motivate here. So we looked at a couple different dependent variables, whether or not a person died in the inpatient visit, and then the total charges for the hospitalization. Then we looked at a variety of different covariates that you can see here. And we looked at descriptive analyses for the variables and regression models for the two dependent variables in this case. Okay, one thing we quickly learned is that the NIS documentation changes a lot across different years. And so an important first lesson is it's really tempting once you download a survey data set, you get the variables you want, it's tempting to just jump into that data set and start doing analysis. It's always very important as a first step to read the documentation so you have a good handle on what those complex sample design features were. Because it turns out there's two different weight variables in this data set. One is weight in pounds. The other is survey weight. And when we first started doing the analyses, we saw weight. We said, okay, let's move forward. Clearly, you see the problem with that. So the final survey weights are in DISC weight based on the documentation. So if you go to this web link, the documentation explicitly says, when you're analyzing these data, use this weight variable for the analyses. And it shows you examples using the code of how to actually do this kind of analysis. The strata are contained in this variable called NIS stratum. And the sampling clusters, which in this collection were hospitals, those were the primary stage units, those are simply captured in HOSP-ID. So an important first step is always to go into the documentation and see what those key design variables are that describe the sampling process for the data user. Okay? So we had to track those down first of all. So our first descriptive analysis was, again, this kind of naive approach where we ignored the design features entirely. So I've included in parallel the SAS code that we use and the Stata code that we use. Again, just being ignorant about everything we just spent the last 2 hours talking about. Okay? So in SAS, we would just use proc freq. There's my data set. There's my variables. I want tables. Done. Okay? If I want means, proc means. Ask for the sample size, the mean, the standard error. There's my variables. Done. Data, I would just use the prop command or the mean command to analyze each of the variables. Okay? Easy to do. We learned how to do this in our intro stat classes, but as you now can see, very dangerous for these data sets. Analysis 2, okay, somebody told me I need to use weights. Let's turn them on. I don't care about anything else. Ignore other design features. Now notice my procedures change. Okay? No longer using proc freq or proc means. I'm using in SAS the survey procedures. These are procedures that have been explicitly designed for everything we just spent the last 2 hours talking about. Okay? Procedures that have been explicitly designed for design-based analysis for finite populations. To read in these weights, these stratum codes, these cluster codes, these replicate weights, and give you appropriate estimates and standard errors using the information that you provided. So it's great now that I'm using survey freq and survey means. It's great that I'm using the weight. Notice how I just add the weight subcommand followed by the name of that weight variable. That's all you have to do to use the weights. Remember the 50% of articles that we just found didn't do this. It's one line of code to do this correctly. Okay. But, as we've talked about, this still isn't correct. We're still not accounting for the strata and the clusters. Okay. So in Stata takes a little bit different tack. In Stata, you can declare the design features globally with one line. So in Stata, it's the survey set command, where you can say what your cluster codes are, what your final weights are, what your stratum variable is. And here in the survey set command in square brackets, I'm only saying what the final probability weight is. That's it. I'm not declaring anything else. And then once I set survey set within Stata, I add SVY : to all of my standard analysis commands. That implements design-based analysis. That's all I have to do. It's one line of code followed by modifying the standard commands with SVY : That's it.
In the state of code, where's the cluster listed?
We're not doing that here. We're being naive still.
So, oh, sorry, I'm wrong.
Yep.
Can you talk a little bit about
Sorry.
I'm sure this is possible with R.
Yes.
Can you just talk briefly a little bit about preferences for which programs are
They give you the exact
better?
same answer.
They all are equivalent.
Yep. They all give you the exact same answer. In R, you just need the survey package.
Yeah.
So Thomas Lumley is the author of that survey package, and R's survey package does everything we're talking about here, and then some. For free. Okay, so still naive, but at least we're getting appropriate point estimates with respect to the sample design. Okay, so we're accounting for these weights on the analysis. Now, back to Barry's question, here's analysis number 3. Okay, now we're doing a fully design-based analysis where we're accounting for all of those complex sample design features. So look what happens to the SAS code. Now we add the weight statement, but we also add the cluster statement and the stratum statement. That's going beyond step 1. Okay? That's saying we want to use, in this case, SAS uses linearization by default. We want our linearized variance estimate to account for the cluster sampling and the stratification that was inherent to this design. That is a fully appropriate design-based approach to this kind of analysis. Okay? Same thing with survey means. We had the exact same 3 variables. In Stata, we don't have to do that over and over again. We just update that survey set command to first list the cluster variable, Haas by D, then the weight in square brackets, then after a comma, the stratum variable as a strata argument. Okay, then we're fully accounting for the stratification, the cluster sampling, and the weight in estimation. Nothing changes about the actual analysis commands that we're using. Okay, so that we're still just adding SVY : in front of all of these commands. And quite honestly, today on September 24th, 2019, Stata is leading the way in terms of how many commands have been adapted for design-based analysis. Everything from structural equation models to multi-level modeling to instrumental variables. Stata has done an amazing job of adapting their base commands to the SVY approach. Okay, so I think of the different software, I have a preference for Stata in that regard for design-based analysis options. Okay, but again, one line of code followed by adding SVY to whatever command you're running. That's all that you have to do. And now the workshop's over. I'm just kidding. Okay? But it's honestly that simple. All the stuff that we just talked about, like how it seems to be a research problem, this is all that you have to do. So let's do the comparison. This is the descriptive stuff for the dependent variables. These are estimated percentages. So in the NIS, key feature here, the weights have almost zero correlation with these key variables. Yep, Jen?
There's a question like earlier you mentioned 2 different types of variance estimation, series and technique or BR.
Yep.
How do we choose the method and how do we incorporate that into data code?
So the question was, if people didn't hear that, if you want to choose between variance estimation methods like linearization or replication techniques, how do you do that? In SAS, in the proc survey freak line, you can see my red dot up here. Maybe I have to do it over here too. In that proc survey freak line, you just have to add the var method option, and SAS gives you 4 different var method choices for the type of variance estimation method. In Stata, there's a VCE option for variance estimation that you can add to survey set, indicating what type of variance estimation you want to use. For these examples, I'm just using linearization as a default, but if replicate weights are available, you can still specify them as part of the code. Okay, any other questions on this code before I go into the results? Okay, So descriptive table. Key message here is that the NIS weights were not correlated with the indicators. Okay, so that's important. You see in this case, the unweighted estimates are basically equal to the weighted estimates. So these are two examples of variables where the weights don't matter. They flat out don't matter for that particular estimate. Okay? However, you see what happens to the standard errors. Okay? 4-fold, 25-fold, 30-fold changes in the standard errors when you fully account for the design features. So while the point estimates stay the same, when you fully account for the cluster sampling and the variability in the weights, you can see the standard errors go up. And notice, in the second column, we are accounting for the variability in the weights. The variability in the weights doesn't really affect the standard errors. What's happening in this case is the cluster sampling dominates the sampling variance. That's what's causing those big increases in the standard errors. So to provide perfectly robust design-based estimates, we'd want to report what's in column number 3. But in this case, a failure to use the weights does not have serious implications. Okay, so we might get lucky if we don't use the weights here. But as a general analysis approach, always look at these correlations. In this case, the correlation was essentially 0 with these two variables. Okay. More means here in this particular case, same kind of pattern. The weights weren't correlated with these variables, but the standard errors did go up substantially. Like look at, for example, age of admission. That standard went up by about 39 times. Okay? So you think about different kinds of estimates, again, the implications of doing this. But weights didn't matter for these particular estimates. So I mentioned the subpopulation issue. When you're using linearization, especially for variance estimation, the message here is don't simply delete cases that do not belong to the subpopulation. Okay, that's the critical point here. The approach to use in practice is to use the built-in subpopulation options that are available in these different procedures. So in Stata, for example, after you say SVY, you can add a comma and then use the subpop option. And in parentheses, what you put there is your binary variable, where 1 indicates cases in your subpopulation, a 0 indicates cases not in your subpopulation. That's it. That's all you have to do. Then Stata will process the entire data set, account for sampling zeros in the variance estimation, and give you appropriate standard errors. If you don't do this and you condition on the data set or something, you again run that risk where Stata flat out won't give you standard errors. If you drop so many clusters that certain strata only have 1 cluster present. And a lot of people will come to us and say, looks like Stata's broken. Like, how come Stata's not completing my standard errors? And it's because of that very problem.
In Stata, where you mentioned before, there's a global option of survey setting the data. Like, let's say you've done that and you account for the stratification, and then you go in some specific procedure or model you're estimating, where you're doing it like only on older adults, for example. Right. You then just use an if statement there, or you have to really get to go specifically apply the
so even in the survey command, if you just added an if modifier, that's exactly the same thing as if you had deleted all those cases before. It's the same mistake. So the simple solution is in all situations, just use subpop, or if you're using SAS, add that domain statement. That's how to set it up. Yep, Catherine?
I'm wondering about missing data into data missing on specific variables or individuals, and how does that feed into this? Do they become part of the subpop value 0?
Yeah, so that depends on how you do. So the question for those of you online who maybe didn't hear that is, what about missing data in defining that subpop indicator? The approach I would suggest is that if they have missing data on the variables used to define that indicator, leave them as missing. Don't recode them as a 1 or a 0, just leave them as missing. Then those cases just get dropped entirely because you don't know how to handle them. And if there's so much missing data that you lose a particular cluster, that's a data producer problem. That's my view on it. So I would not just blindly recode missing values to a 1 or a 0 on that subpop indicator. I would leave them as missing. Other questions? This is critical, but it's another thing that's easy to fix. That's the point here. All of Stata's survey procedures have this subpop option. All of SAS's procedures have this domain option. Just add that option if you're analyzing a subpop. It's really that simple. Okay. Regression approach. Here's what these procedures look like, ignoring the design features altogether, okay? So in SAS, I'm using proc survey logistic just for comparable standard errors. You could also use proc logistic. I didn't have to use survey logistic here, okay? But notice there's no weight statement, no stratum code, no cluster code. In Stata, I'm just using the logit and the reg commands. That's it. So no SVY, no survey set, just the naive approach where we completely ignore all these design features for a logistic model of whether or not there was a death, and then a linear regression model of natural log total charges for that visit. Okay, adding the weights, same idea. I just add the weight statement, okay? Or I add the P weight in square brackets for Stata, and I make sure that I use the SVY colon commands. So no different from what we talked about with the descriptive stuff. But this just shows how easy it is to implement these design-based procedures with regression models or other kinds of multivariable models. The code is the same. You're just modifying whatever regression command you're already using. And in the fully design-based approach, the appropriate approach, in SAS, I just add those three statements. In Stata, I again add the cluster ID, add the stratum variable, and again use SVY logit and SVY reg. Questions? Yep.
You mentioned a couple times that there's some debate over whether to use these.
Yep. We're going to come back. There's a whole section on that. We'll take another break here, but I'm going to spend some time.
One question I still don't see in Stata where you're defining the cluster.
Hosp ID. You declare the cluster code first.
Okay.
Yep. So whatever variable contains your cluster codes, usually your primary stage units, that goes first right after surveys. Other questions about this code for the regression models? Yes. Any other questions? Yep.
So, are these examples from like cross sections, something like longitudinal data, HRS, the weights change, and like survival analysis won't let you use?
That's a great question. So what we're talking about right here, like, it's like the problems are on steroids. You're talking about longitudinal data because the weights, like you said, they're changing over time. You have to account for time varying weights. You have to account for weights that capture different patterns of attrition. In longitudinal studies, it becomes doubly important to account for the weights. Otherwise, you're going to get a completely misleading picture of what trends look like in the population. Yep. So I don't have any longitudinal examples specifically, but in this book up here, we have a whole chapter dedicated to how to use weights appropriately in longitudinal studies. Yep. Okay, other questions about this regression code?
Okay, so one thing that I'm confused about is your discussion of the subpopulation.
Yeah.
So imagine that we were doing a study where we specifically had data on 10,000 people, but we wanted to do that same logistic regression on half of those people. Right. So you're saying then that you would make a binary variable for those who are included and 0 for those who are excluded. And then you would add that to the first set command.
Right. So you go through that data management step of creating a 1-0 variable for your for the cases there, and then instead of just using SVY logit, so what I would say is SVY comma, autocorrect, subpop, and then like subind or whatever you want to call it. All you have to do is list the name of that indicator. What I was saying that Jeff just mentioned about subpop analysis that you don't want to do is this. Use SVY colon, ignore the subpop option, and at the end of that regression model specification, say if subind is equal to 1. That does the exact same thing as if you had physically deleted those cases from your data set.
So I guess where my question then comes in is, what if the way that you're making this sampling inclusion or exclusion criteria is based on whether they have a particular response to one of the variables in your logit command? So I don't know, let's say anyone who's missing age is definitely going to be excluded from our study. Right. So they can definitely have a 0 versus 1 on the subpopulation variable, but they're going to have a missing on the age variable. Does that matter?
Yeah, just that defines what cases are ultimately going to be used to fit that model to begin with. The thing you have to be careful of is that, like, just as a simple example, if I wanted my subpop to be restricted to females only, like I can no longer use female in that model. That's the issue. So as long as you have some variability in age, for the subpop that you indicated, regardless of missing values, you can still treat age as a covariate.
Okay, so then my last final sort of.
That's okay.
Is, so really the reason that we're even including this subpopulation command for those that we're not interested in having in our logistic regression in this case is because we want to know what their variables are on the cluster, the strata, and the weight.
The most important thing is to use the subpop command. In a lot of these examples, if you make this mistake and do if or something, and you use the subpop command, the results will be exactly the same. What you want to protect against is when you delete entire clusters. That's the issue. The results won't be the same if you physically delete a cluster that had no subpopulation units. The appropriate approach is that to all of these estimates, that cluster contributes a 0, as opposed to being ignored entirely. That's the distinction. So when you look at variability between clusters, that cluster just contributes a 0 to all the totals that are used in estimation, as opposed to being ignored entirely. That's the main reason that we want to do that.
Yeah, I guess the reason I'm having difficulty is because if you use the PSID, which is extremely complex, there's like 80,000 different respondents across every given year. And if I really only want to look at people who are in PSID gened families, then I have all these non-PSID gened individuals who, like I have 60,000 of them. So in this case, I would assign them a 0 on the subpopulation variable.
Exactly.
So that we still get their information.
Get their information.
Those other.
Yep.
See, but some of them don't have weights though. So some of them don't have individual level weights.
If they don't have weights, they're going to get dropped either way.
Okay.
People without weights won't get used, but if there's a sampling 0, you just want to know how much sample size came from that cluster that had a sampling 0. You need that information to describe the design.
Is it specific only to clusters, or does it also apply to strata?
It's mainly an issue for clusters. If Stata detects a stratum that has no subpopulation present, Stata takes the approach that you would never have subpopulation present from that stratum, so it drops that stratum entirely. That's a Stata thing. Okay? SAS still just processes 2 sampling 0s and a 0 ultimate variance contribution from that stratum. That's slightly different. It's not going to change estimates that much, but in terms of Stata, the developers of Stata's survey procedures just said, if there's a subpopulation that doesn't appear at all in an entire stratum, we're just going to completely remove that from the picture.
Great. Thanks much.
Yep.
So I'm confused with the difference between, okay, if you have 2 clusters in strata, and one of them does not have a subpopulation. So if you just use a subpopulation indicator, when it tries to compute the within strata cluster,
When the within stratum variance.
Sorry. So basically it ends up with a 0 for that strata?
Exactly. So when you're using linearization, the default, everything from an odds ratio to a linear regression coefficient, when you calculate variances of those estimates, it's working with variances of totals.
Okay.
That's the way linearization is working.
Okay.
So when the software calculates that variance of these different totals, within that stratum, there's going to be one total of 0 and another total of something else. And that means that that stratum can contribute a variance estimate to your overall variance calculation.
But it should give you a within cluster variance.
Not within. We're not worried about within. We're worried about between.
But between would be, it would set it to 0?
The between variance would be based on a total of 0 and a total of something else. So the variance of those 2 values is going to be a non-zero variance.
Okay. So in a sense, it's taking the average of cluster 1, if that's got the subpopulation, and the average of clusters 2, which doesn't have the subpopulation.
It's not taking an average. I think you're overcomplicating it. It's just taking a 0 from the cluster that doesn't have any subpopulation. That's the total. It's taking a non-zero total from the cluster that has some subpopulation. Those are 2 values. Call it 100 and 0. It calculates the variance of those 2 values and contributes it to the overall estimate.
Okay, so in a sense, see what confuses me is, for that, in a sense, you're basically saying that there should be a variance for that
Exactly.
cluster.
Because you happen by random chance to have a sampling 0.
Okay.
In other hypothetical replications of the sample, remember, we're talking about the sampling distribution.
Okay.
In other hypothetical replications, there might not be a sampling 0.
Okay.
So we have to account for that 0 as part of the variance estimation.
Okay.
Yep. Okay, other questions about this code here? Jen, any questions on the chat? Okay. Okay, so we'll finish up this example and then we'll take a break here. Let me get back to the main show. Okay, so here's the linear regression analysis. So again, this was predicting the natural log of total charges. So again, this is where the weights basically were not informative. So you see that regardless of whether you use the weights or not, you see essentially the same coefficients. All that's changing is the standard errors of those coefficients when you account for the design features. So much like the descriptive estimates, the weights also were not informative about the coefficients in this data set. As we saw earlier with the Vertis, they can be very informative about regression coefficients. So it will vary from one context to another. But as a general approach, it's important to consider things both ways. And we'll come back to that should we wait or should we not wait question after the next break. Okay, so that was the linear regression model. Here's the logistic regression model. A couple of slight changes here, nothing major. Again, the big changes are in terms of the standard errors. Okay, so same kind of pattern across all these NIST estimates for these particular variables. So again, to fully reflect what's happening with the design, what's really happening here is in terms of the standard errors. Again, we just want to make sure to report column 3 in terms of the standard errors to reflect the sample design features. Okay? So major takeaway points here from these analyses. The weights in this case were not informative about the estimates of interest, but again, this will not always be the case. This is just one example data set where the weights were not correlated with the variables that we were working with. But in this case, accounting for the strata and clusters did matter for inference, especially when forming confidence intervals, because the standard errors got a lot larger. So it's not enough to just use the weights in these kinds of analyses. These were big samples. So the national inpatient sample is huge. For that constructing confidence intervals, the degrees of freedom were going to be about 7 million if we ignored the design features. It's a huge sample. Okay? When you fully account for the complex sample design, it becomes 886. So it's still a lot of degrees of freedom for variance estimation, but I asked the question, what again if you only had 30 clusters and 15 strata in a given complex sample design? That becomes a very different value and a very different critical t-value for forming the confidence interval. Okay, now another thing we learned in looking at the NIS data is that because of these issues in part, beginning in 2012, all the national inpatient sample microdata are self-weighting. What that means is that every weight is equal to the same value. Okay? We started off looking at later versions of NIS data. This is again why it's so important to read the documentation. And I was looking at these correlations of the weights with all the variables, and it was like 0, 0, 0, 0. I was like, what's happening? And I just looked at the mean and standard deviation of the weights, and the mean was 5, and the standard deviation was 0. So I don't know what the significance of 5 is, but if you look at these data sets, everybody has a weight of 5. The self-weighting sample. So that means as a secondary analyst, you don't need to worry about the weights. The people designing the sample are telling you that everybody has the exact same weight. So you don't need to worry about the weights in analysis. But as I say here, this does not mean that you can ignore the sampling strata and clusters in variance estimation. So just because that you hear that a probability sample or a complex sample is self-weighting, that doesn't mean that the other design features don't need to be accounted for when you calculate your standard errors. We still want to make sure to account for those in that case. So like just as an example, on the next slide, 2 different approaches based on the 2012 plus data. In approach 1, again, I'm ignoring weights in all cases because they don't matter. Everybody has the same weight. Okay? So weights don't matter here. In approach 1, I just look at an estimated mean for these different variables, ignoring the strata and the clusters. There were 196 strata and 4,378 hospitals. In approach 2, I accounted for the strata and the clusters, for example, using survey mean. Look what happens to the standard error of the estimated mean total charges. Again, you see this massive effect of the complex sample design on the standard error. So the point estimate is not being affected. What's being affected is the standard error that we're ultimately using for inference, because now we're reflecting that between cluster variability in the variance estimation. That's what leads to that big change in the standard error. So we want to report these robust standard errors, robust confidence intervals that reflect all these aspects of the sample design before we make our ultimate inferences. That's the key message here. Okay? So it's not just enough to hear that a survey is self-weighting, that you can ignore everything. We still want to account for these features when we report our standard errors. Okay? Okay, so I think that's a good breaking point. Let's take a break till about noon, and then I'm going to pick up with additional descriptive, tests of association, regression models, and we'll come back to that issue of how to compare models fitted with and without weights and talk about some practical strategies for dealing with that. So why don't we take another 10-minute break, and we'll start back up right at noon.